Well, L'Hopital's rule is a tool that allows us to knock out limits quickly and effectively. Let's talk our way into it to see whether we actually still need to do that, because we really haven't looked at limits for a while now. So, we know that computing limits is rather cumbersome, right? I mean, we were very happy once we had the differentiation rules, so we didn't have to use difference quotients anymore. And the reason it's cumbersome is because the algebra takes a long time. But then again, we also mainly use limits to put derivatives on a solid theoretical foundation. And so, I mean, since then, how often have we used limits and how often have we used derivatives? Still, we can't just abandon limits, because limits at infinity tell us about the long-term behavior of a function, and that is something that is typically interesting in models. You want to know whether the object or the mechanism stabilizes or not. And in some models, we're also really still interested in what happens near a point where we divide by 0. So limits will stay with us. They're not as central to calculus as derivatives and integrals. They're the foundation for both, but once we've got derivatives and integrals, we work with those. But they will stay with us in some capacity, and so it would be nice to have a tool that simplifies the limit computation. Okay, let's take a look at an example. Here's a quotient of two quadratics. And you know, well, I mean, when we computed limits, you'd either do the x plus h and let h go to 0, or you look for a factorization for a cancellation. Let's magnify this. And what we see is those two quadratics. Of course, they go through 0 at 2, otherwise the limit is rather easy to compute. And what we see is that as we magnify these functions, because they're differentiable functions, under sufficiently high magnifications, these functions start looking like straight lines. Well, let's see if we can compute the limit of the quotient of the tangent lines. So the tangent line of the numerator, f of x equals x squared minus 6x plus 8. Well, you take the derivative, that's 2x minus 6. The derivative at 2 would be 2 times 2, which is 4 minus 6, which gives us negative 2. And so the tangent line of f at 2 would be 2 times x minus 2. It has got the right slope. And it is 0 at 2. That should be negative 2 there. Hang on just a minute. Okay, now it's a negative 2. We find the tangent line of g of x at g of x equals x squared minus 4. That would be the g prime equals 2x, and the derivative at 2 is 4. And the tangent line is 4 times x minus 2. Again, it's 0 at 2, just like the function, and it's got the right slope. So the limit of the quotient of the tangent lines, well, you just cancel the x minus 2's, and the limit is negative 1/2. And if we compare that with the limit of the actual quotient, well, you factor the two functions, and x squared minus 6x plus 8 is x minus 2 times x minus 4, and x squared minus 4 is x plus 2x minus 2. The x minus 2's cancel. We get the limit of x minus 4 over x plus 2, and as x goes to 2, that ends up being negative 2 over 4, which is negative 1/2, and that's just the same, right? Now, that's not an accident. I mean, from the picture, we already saw that that shouldn't be an accident. And, well, here's the theorem. It's L'Hopital's rule, and when f and g are differentiable functions, and a is a real number, or infinity, or minus infinity, and if the attempt to compute the limit of the quotient f of x over g of x at a leads to an expression of the form 0 over 0, or infinity over infinity, which are the first two examples of indeterminate forms that we're seeing here, then the limit of the quotient f of x over g of x is the same as the limit of the quotient of the derivatives f prime of x over g prime of x. And that's provided that the limit on the right side exists, and if the limit on the right side doesn't exist, then the limit on the left side doesn't exist either. This rule applies to one-sided limits too, so if we can only approach from one side, that's not a problem. And the only problem really is we must sure we don't confuse this with the quotient rule. Typical mistake that happens, that I've seen happen on tests, is that people use L'Hopital when they should use the quotient rule, or they use the quotient rule when they should use L'Hopital. Well, they're two different things. Okay, so proving, well, we can prove not the whole thing, but at least a special case. So let's consider the case that a is a number and f of a equals g of a equals 0. So it's a quotient 0 over 0. Then the limit of f of x over g of x is the limit of f of x minus 0 over g of x minus 0, which is the limit of f of x minus f of a divided by g of x minus g of a. And now we can use the mean value theorem, which says that f of x minus f of a is f prime of cf for some cf between x and a times x minus a, and g of x minus g of a is g prime of cg for some cg between x and a times x minus a. Now the x minus a's cancel, we get the limit of the derivatives, and as x goes to a, cf and cg go to a, and we get the limit as x goes to a of f prime of x divided by g prime of x. Okay, that's the end of that story. That proof is a little unclean here, because if cf and cg go at the wrong rate, at significantly different rates towards a, this need not work. There is a generalized mean value theorem that says we can choose the same cf and cg. We're not going to go that deeply into the theory, so we'll just be okay with this quick and unfortunately slightly dirty argument. Okay, so let's look at some examples, and well, right now L'Hopital's rule is made for quotients, so find the limit as x goes to 0 of sine 5x divided by 2x. Well, if you follow L'Hopital's rule, you realize this is 0 over 0. You take derivatives, you end up with the limit as x goes to 0 of 5 cosine 5x divided by 2, and that's 5 halves. Does that really work? Well, if we're looking at the graphics, here's the function, and the limit is 5 halves. Now that was a lot quicker than what we did at the beginning of the class, and in fact, the limits of functions, of quotients that involve trig functions, are really hard. You can do them with pattern recognition after you know what the limit of sine x over x is, or typically what you do is you use L'Hopital's rule. So here we are. We already have conquered a problem that would have been rather nasty before. If we're looking at problems that we had before, like a limit as x goes to 1 of x squared plus 2x minus 3 divided by x minus 1, well, let's see. At 1, that's 0 over 0, so here's the limit. We find the limit of the derivatives, which the derivative of 2x of x squared plus 2x minus 3 is 2x plus 2. The derivative of x minus 1 is 1. So the limit of that as x goes to 1 is 4. Is that right? Well, yep, here's the function, here's the whole, and the whole is at height 4. Good. Compute the limit of the quotient of two quadratics. Well, that's where things got really nasty in our computations earlier. Well, let's see. When x goes to negative 3, we get 9 minus 12 plus 3, which is 0. And here we get 18 minus 6 minus 12, which is 0 also. So L'Hopital's rule can be applied. It's 0 over 0. So we take the limit. The derivative of x squared plus 4x plus 3 is 2x plus 4. The derivative of 2x squared plus 2x minus 12 is 4x plus 2. If we plug in negative 3, we now no longer get 0 over 0. We get negative 2 divided by negative 10, right? And that is 1/5. And that's 0.2. And if we look at the graphics, well, here's the function, here's negative 3, and here's height 0.2. Great, works rather well, doesn't it? Let's see. Now, those were always ugly when we computed limits, right? Because that's where we had to expand with root x plus root 8. We had to rationalize the numerator or denominator, in this case the denominator. Well, let's see. At 8, it's 0 over 0. L'Hopital applies. So we take the limit of the derivatives. The derivative of x minus 8 is 1. The derivative of root x minus root 8 is 1 over 2 root x. That's the limit as x goes to 8, 2 root x. That ends up being 2 times root 8, which is 4 times root 2. That's approximately 5.65. And graphically, at 8, here's 5.6 something. Yeah, it works. If we compute now limits that we couldn't handle before, I mean, here's where without series, and we don't have series yet, I don't have any cancellations, right? But what I do see is, as x goes to 0, x squared goes to 0, e to the x goes to 1, x goes to 0, so 1 minus 0 minus 1, it's 0 over 0. Well, again, we just take the limit of the quotient, we compute the derivative. Derivative of x squared is 2x. The derivative of e to the x minus 1 is e to the x minus 1. Oh boy, we still can't compute the limit because this is still 0 over 0, but L'Hopital's rule applies to that one too. So we take the limit, take the derivative again. Derivative of 2x is 2. Derivative of e to the x minus 1 is e to the x. This is the limit which we can compute now because this ends up being 2 over 1. That's 2. And graphically, well, here's the function, and at 0, that thing really has a hole at height 2. Great. What else can we do? Well, let's take a look at another limit of quadratics. Let's see, at 2 we get 4 minus 10 plus 6, that's 0 in the numerator, and we get 4 minus 8 plus 4, that's 0 in the denominator, so we can apply L'Hopital's rule. And the derivative of x squared minus 5x plus 6 is 2x minus 5. The derivative of x squared minus 4x plus 4 is 2x minus 4. Good. What do we get? We get a negative 1 in the numerator, and we get a 0 in the denominator. So that limit does not exist, and that means that the limit of the original quotient also does not exist. And graphically, if we're graphing the function, we see we've got a vertical asymptote at that point, which means there are infinite limits, and in the parlance of limits, as long as we don't deal with infinity, that just means that the limit doesn't exist. Okay, what else do we have? Okay, this is the limit as x goes to infinity. And if we take the limit as x goes to infinity of x to the 7th plus 4x to the 5th minus 13 divided by 3x to the 7th minus x to the 6th plus 12x squared, well, we expand with 1 over x to the 7th. We end up with the limit being the limit of x to the 7 over x to the 7, which is 1, 4x to the 5th over x to the 7, which is 4 over x squared, negative 13 over x to the 7 right here. 3x to the 7 over x to the 7 gives us 3. Negative x to the 6th over x to the 7th gives us negative 1 over x. 12x squared times 1 over x to the 7th gives us 12 over x to the 5th. And as x goes to infinity, this guy, this guy, this guy, and this guy goes to 0. So the limit is 1/3. Where did we use L'Hopital's rule? We didn't. And we shouldn't, because if we wanted to do this, we would get infinity over infinity for the first 6 derivatives that we take, and I really have no patience to take all those derivatives. So it turns out for certain limits, really, the old way to compute the limits still is preferable. And of course it gets the right result because, well, here's 0.5, here's 0.25, so 1/3 is about there, and that's what the horizontal asymptote of this function should be. Let's take a look at another limit at infinity. And let's just see if we could use L'Hopital's rule here, just to see what could also happen. That's the most pathological thing that can happen with L'Hopital. So, well, it's infinity over infinity, so we can apply L'Hopital's rule. Take the derivative of the numerator, which is 3x squared. Take the derivative of the denominator. Okay, chain rule, right? 1 over 2 times what's inside, times the derivative of the inside, which is 6x to the 5th. You simplify, 6 over 2 is 3, so you get 3x to the 5th here. The 3's cancel. You get an x cubed in the denominator, and this thing moves into the numerator. So we end up with, okay, I canceled the 3 against the 6 and kept the 2's, alright, but we end up with the limit as x goes to infinity, ultimately of root x to the 6 plus 1 divided by x cubed, which is exactly the reciprocal of this thing. Well, guess what? If you use L'Hopital's rule on that, you end up with the same thing that you started with. So here's one where L'Hopital's rule isn't plain tedious, it just doesn't work at all. In the old-fashioned way, of course, you expand with 1 over x cubed. You get the limit of x cubed over x cubed divided by root x to the 6th over x to the 6th, because this is square root x to the 1 over x to the 6th, right? And so that gives us the limit as x goes to infinity, 1 over square root 1 plus 1 over x to the 6th, and that's 1. And if we graph this function, yep, the horizontal asymptote is at 1. Okay, now let's look at indeterminate forms. What we've done so far is we've looked at quotients. I think I've pulled many of those quotients actually out of the first limit presentation that we worked our way through, and that shows that as long as we're allowed to use derivatives, L'Hopital's rule really replaces a lot of tedious stuff. We've also seen that L'Hopital's rule allows us to compute some things that we couldn't compute with elementary methods. Now let's take a look at indeterminate forms. A limit computation which, when we evaluate all terms, when we're plugging in the number, just leads to 0 over 0, or infinity over infinity, or 0 times infinity, or infinity minus infinity, or 0 to the 0th, or 1 to the infinity, or infinity to the 0th, that is called an indeterminate form. Well, okay, we've seen these two already. 0 times infinity, if the first factor goes really fast to 0, then it won't go to infinity. If the second factor goes really fast to infinity, it could still go to infinity. So that's indeterminate. Infinity minus infinity, well, depending on how fast these go, that could be any number also. 0 to the 0th, algebraically, is typically defined to be 1, but depending on how fast things go here, this exponent could still pull this, or if the base goes really fast to 0, then this could be pulled towards 0, and if the exponent goes fast enough to 0, well, then it typically gets pulled to 1, but it still is indeterminate. 1 to infinity, well, if this goes to 1 from above, so it's slightly bigger than 1, and you've got a really big exponent, it could pull away towards infinity. And infinity to the 0th, well, if the base goes really quick to infinity, then the raising to 0th doesn't pull it back to 1. So there's all sorts of things that could happen with these things. These cannot be just resolved with some quick rule that says this is always the following. For example, we want to compute the limit as x goes to 0 of 1 over sine x minus 1 over x. Well, that's infinity minus infinity, and actually what I would like to have here is I would like to have the right-sided limit, because otherwise we might have some trouble with negative signs. Let me take a look at that real quick. There, now it's a right-sided limit. I wanted to be careful here with the negative signs. It actually turns out that the limits from either side are the same, but technically, because of the trouble with negative signs, we would really have to compute them separately, even though the computations are basically the same. Okay, right-sided limit of 1 over sine x minus 1 over x. It's an indeterminate form. It's infinity minus infinity. And, well, what do we do? This is not a quotient. We can't apply L'Hospital's rule, but we can, of course, take a difference of quotients and turn that into a quotient by finding the common denominator, which is x times sine of x, and so then we get x over x sine x minus x sine x over x sine minus sine x over x sine x, and so that's the right-sided limit at 0 of x minus sine x divided by x times sine x. Now we have 0 divided by 0, so we take the derivative, which is 1 minus cosine x in the numerator, and in the denominator we use the product rule, right? The derivative of x is 1 times sine of x plus x times the derivative of sine x, which is cosine x. And at 0 we still end up with 1 minus 1 divided by 0 plus 0, so we use L'Hospital's rule again. The derivative of 1 is 0, the derivative of the negative cosine is function is the sine function, and here we get the derivative of sine x is cosine x. Here we use the product rule again. The derivative of the cosine x is negative sine x, so we get minus sine x times x, plus the derivative of x is 1 times cosine x. Now we have 0 in the numerator, and we have 1 minus 0 plus 1 in the denominator, so that's 0 divided by 2, so a 0 in the numerator just gives us a limit of 0, and the graphics actually bear that out, and you can see even the two-sided limit is 0 here, but we would technically, because we're coming in from the negative side, we would have had negative infinity minus negative infinity as an indeterminate form. It would have technically had to do a separate computation. Okay, what else can we do? We can look at things like x times e to the negative x, right? The old rule of thumb that exponential growth or exponential decay beats polynomial growth. That's something we can justify now. So this is an indeterminate form of the form infinity times 0. Well, take the limit, turn it into a quotient. Now it's infinity over infinity. L'Hospital's rule applies. The limit of the derivatives is the limit of the derivative of x is 1, the derivative of e to the x is e to the x, so it's the limit of 1 over e to the x, which is the limit as x goes to infinity of e to the negative x, which is 0. And again, graphically, that's what happens. The x first tries to push this up, but as soon as the exponential decay really gets going, this function decays towards 0 very, very rapidly. And this is something that you can do for any polynomial, because after you take enough derivatives of those polynomials, you end up with something divided by the exponential. So, polynomial divided by exponential will always go to 0 at infinity. Now let's take a look at something else here. Take the right-handed limit of the square root of x times the logarithm of x. Okay, what is that? That's infinity times minus infinity. Well, the minus really doesn't matter that much. We could just factor that out. And so what do? Well, we need to turn that into a quotient, and there are two possibilities to turn that into a quotient. We can make that the limit of root x divided by 1 over the logarithm of x, and we'd have really ugly derivatives. What we really want to do is we want to get rid of the logarithm, so it's probably better to write this as the limit of the logarithm divided by 1 over root x, or x to the negative 1/2, because we know this one becomes simpler when we differentiate it. This one is 1 over x. The derivative of this one is 1 over x, whereas this one is just another power in the derivative. Okay, so take the derivatives, which is allowed because we end up with minus infinity divided by infinity now if we take the limit at 0. We take the derivative, we get 1 over x divided by power rule here, negative 1/2 times x to the negative 3/2. That I first would want to simplify, and, well, because we've got a negative exponent here, we end up with, well, okay, 1 over negative 1/2 is negative 2, x to the negative 3/2 is x to the 3/2, 1 over x is an x in the denominator. Now we can cancel. This ends up being, well, okay, the cancellation I forgot to type. This is the limit as x goes to 0 of negative 2x to the 1/2, right? And then that ends up being 0. And that's indeed what the function does. Look at this. The logarithm really tries to pull the function away, and then at the last minute, at the last hour, the square root pulls it back to the origin. What else can we do? Well, we can look at 0 to the 0th. Well, that's not a quotient. That's not something that we can turn into a quotient once we, or by algebra. So the first thing we do is we compute the limit of the logarithm. Okay, the logarithm of x to the root x, that's root x times logarithm x, and we've just computed that that limit as x goes to 0 from the right was 0, and so that means that the limit of x to the root x as x goes to 0 from the right is the limit of e to the ln x root x, right? That's just realizing that that x to the root x is e to the ln x to the root x, which I then just plugged in. And we know that that limit is, or we know that the exponential function is continuous, so we can pull the limit into the exponent. And we know that that limit in the exponent is 0, so you get e to the 0th, which is 1. And that turns out to be the case. Again, it tries to pull away, but then at the last minute, it actually pulls towards 1. Okay. And we can also do that for limits at infinity. So let's take a look at a limit where we have, what do we have? We have 0 to infinity. Well, when x goes to infinity, 1 over x goes to 0, and small numbers raised to large numbers become even smaller, and hence the limit is 0. And that's because, yeah, right, 0 to infinity is not an indeterminate form, right? That was actually not on the list. And so, yeah, I hope it was not on the list, otherwise I'd have to correct the slides, and I would post correct slides. But yeah, 0 to infinity, when something gets small, when something is smaller than 1 and you raise that to a large number, that's going to go to 0. And if the number itself goes to 0 too, it just goes to 0 even faster. So be careful. Sometimes looks like an indeterminate form, and yet you don't need to apply L'Hospital's rule. Okay, graphically checked. Yeah, I mean, that thing just bounces to 0, and that's it. Okay, now let's also work with parameters. I've decided on these later slides I'm going to take the sermon on why we need to work with parameters out. I mean, by now you've been in college for a little bit at least, and you probably have seen in your other classes that you have to deal with parameters. So let's take a look at this one. Limit as x goes to infinity 1 plus a over x raised to the x. So this is now 1 to infinity, and that is an indeterminate form. And so again, because it's a power, we first take the logarithm. So limit as x goes to infinity of the logarithm of this thing. Well, the logarithm pulls the power out, right? Sorry for the unclean mark in here, but basically that's the limit as x goes to infinity, x times ln 1 plus a over x. And we need to turn that into a quotient, and we do that by taking the limit as x goes to infinity, ln 1 over 1 plus a over x divided by 1 over x. if you did x over 1 over the ln, you would get some really ugly expressions and realized, well, maybe it's better to try it the other way. But here now we take derivatives. Okay, the derivative of the logarithm is 1 over whatever is inside, which is 1 over 1 plus a over x, and then times the derivative of the inside. The derivative of 1 is 0. The derivative of a over x is negative a over x squared. The derivative of 1 over x is negative 1 over x squared. You can see here the negative 1 over x squareds actually cancel. And so this is the limit as x goes to infinity of a, which is what remains in the numerator, of a over 1 plus a over x. As x goes to infinity, that goes to a. And so that means that the limit of 1 plus a over x raised to the x is the limit of e to the ln of what we had previously. And we pull the limit into the exponent, and that's e to the a. And that is actually rather nice. That is a standard formula for the exponential function, which we can now prove fairly quickly. Now, this is not how the exponential function is represented numerically inside a computer, but it is sometimes, basically whenever these kinds of limits come up, we know now that, yeah, we're defaulting to the exponential function. Graphically speaking, I should have said which a I'm using here, or which, well, let's see, what went to infinity. X went to infinity, so the input actually is a here, not x. But basically, as I let the exponent go to infinity there, these functions get closer and closer to the exponential function. All right, that's L'Hopital's rule. Basically what it does for us is it shows us a couple of computational tricks that probably aren't too bad to have, because it keeps us working with more algebra, and remember, independent of whether you ever again have to compute a limit. And if you're in engineering, odds are you probably don't. And if you're in the sciences, specifically in physics, odds are only slightly higher that you do. But nonetheless, the techniques that we have here, the pattern recognition, the various ways in which we can turn functions around in order to turn them into something that we can digest with theoretical methods, that's what ought to stick with you, as well as, of course, as you're doing homeworks and as you're passing tests that involve this stuff, the manipulations for L'Hopital's rule itself. And then, of course, it is rather beautiful to see how the use of tangent lines in that zoom that we had helps us to compute limits that previously we could not compute directly. Okay, so with that, you can knock out plenty of limits on your homework. Get to it.